Hi everyone, welcome back. In this video we will practice drawing electron like molecular geometries and Lewis structures, and discuss briefly about electronegativity to help us determine if we have polar covalent bonds, nonpolar covalent, or something that might be ionic. So electronegativity is an atom's intrinsic ability to draw electrons towards itself. There's some atoms that just want all of the electrons. And the most electronegative element on the periodic table is fluorine. So that's how I like to remember. As long as I know the most electronegative element, then I know that electronegativity increases as we go across, and it also increases as we go up. And this is a table that shows us the different values. You notice that the noble gases are not even present. They really just don't have any electronegativity because they have their octet and they are happy as can be. So they're the least electronegative. And these little values here help us to determine if we have a specific bond. We can calculate the difference in electronegativity to determine if that bond would be nonpolar covalent, polar covalent, and ionic. And so the rules for that is if you have a value of 0 to 0.4, then you're looking at something that is nonpolar covalent. If you have a value of 0.4 to 1.8, then we're looking at something that is polar covalent. The charge distribution between the bonded groups is more different than it is for nonpolar. And then if you have something that is greater than 1.8, then that is something that might be ionic. Now, this is very kind of just a guide, right? We will learn in future videos that polarity is not something that is black or white. It's more of a continuum. So there are molecules that are more polar than other molecules that are also polar. So there's level of degrees of polarity, so to say. So when we look at 0.4 and 0.4, that can be a little confusing to beginning chemistry students. But as you practice more problems, you will become familiar with all the different types of bonds that show up. So for example, I'm an organic chemist by training, and so I work a lot with carbon and hydrogen. Now, the carbon bond or carbon atoms, 2.5 electronegativity, hydrogen's 2.1, 2.5 minus 2.1 is 0.4, and therefore we're right here. Is this a nonpolar covalent bond or a polar covalent bond? And so carbon hydrogens are identified as nonpolar covalent. Okay, and so when we get to the subject of organic chemistry, I'll do a brief intro on organic chemistry for general chemistry. So when we get to that and you see carbon-hydrogen bonds, you'll remember okay, these are nonpolar covalent bonds, whereas carbon-oxygen bonds, there's a much greater difference in electronegativity of 1.0. Those will definitely be polar covalent. So this is something you should have, learned about in first semester general chemistry, electronegativity. It's a concept that's really important for you to master so that when you get to intermolecular forces, having this general knowledge will help everything make sense. In addition, this concept shows up throughout all fields of chemistry. So in organic chemistry, electronegativity is discussed quite often. Now, I have students ask me often, do we need to memorize these electronegativity values? And the answer is no. But it is important for you to know that fluorine is the most electronegative element on the periodic table. And it's equally important to remember and practice problems so that you can remember different types of bonds. And like anytime you run across a carbon-hydrogen bond, you're like, that's definitely nonpolar. Or a carbon-oxygen bond, that's definitely polar. So it's through practice that you will become aware of the different types of bonds and their patterns of polarity or nonpolarity or even ionic. Okay? So let's just go ahead and let's just practice some examples together. And if you want to pause this video at this time and kind of draw the molecular geometries and determine if it's polar or nonpolar on your own, that would be great practice, and then come back and check your work. All right. So the first thing you want to do when you're building a molecule is you want to count the total number of valence electrons. And you can do that by looking at the periodic table and the group numbers. So xenon is in group 8A, so it has 8 valence electrons. Oxygen has 6 valence electrons. It's in group 6A. And then fluorine has 7. But there's 4 of them, so we have to multiply that. And this all adds up to 42 valence electrons. Remember, valence means the outermost electrons, and those are the electrons that we're going to use to form bonds and to build this molecule. All right. So we always put the least electronegative atom in the center, and we put the outside atoms, the more electronegative atoms, on the outside. And right now, we don't know what the molecular geometry is. And so that's why the Lewis structures do not always represent the correct bond angle. We're not drawing any bold or dashed lines. We're not drawing that 3D representation yet because we're trying to figure out what is it, right? So when you draw Lewis structures, draw the skeleton first, just the central atom, and then bond it to all the outside atoms. And then you fill the outside atom's octet first before you even look at the central atom. And you count how many electrons you have drawn in. And so 1, 2, 3, 4, 5, 6, 7, 8. And so something with this kind of, bond and then all the lone pairs, that's 8. And there's 1, 2, 3, 4, 5. 8 times 5 is 40. And we have 42 valent electrons to work with. So if you have any leftovers, then they can go on the central atom. That's if and only if you have leftovers. So we have them on the central atom here. Now, it turns out, if you remember calculating formal charge, and if not, then make sure you please review that. But if we're looking at oxygen, oxygen normally has 6 valence electrons. 2 of them are bonded, so we say bonded electrons divided by 2, and then minus the number of free electrons on, so these are the 2 bonded electrons, and then minus the 6 electrons that are non-bonding, and that's -1. So right now, oxygen has a -1 formal charge, and you don't always have to do this calculation. If you recognize an oxygen with a single bond and 3 lone pairs around it, that's a -1 formal charge. Now, the formal charges should all add up to the overall charge, which in this case is 0. And so something in here has a +1 formal charge, and I'm going to try that out with the xenon. So xenon normally has 8 valence electrons, and it looks like in a free atom, and it has 1, 2, 3, 4, 5, so 10 bonded electrons divided by 2, minus 2 of those free non-bonding electrons, and that is equal to plus 1. Now, the reason why I'm doing this, and you're going to see it in the next example here, is that if a molecule can minimize formal charge, it will. And the reason why I say, like, if it can, is that some central atoms cannot break the octet rule. And I'll go over that in the next example. But xenon obviously can. I mean, it has already 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's really low on the periodic table, which means it has a greater principal quantum number n and more orbitals to place all of these electrons. And so there are some cases where that can't happen. For example, carbon can never break its octet rule because it only has s and p orbitals, so it can't fit more than those 8 electrons. But I'll talk about that again in the next example. Well, xenon can. And so the way right now as it stands, it's got a plus 1 formal charge. The way that it can minimize its formal charge is by forming a double bond between xenon and oxygen. And so the true structure, and we're still in Lewis dot structure, we haven't done molecular geometry, but we look like this, where 2 of those electrons that were located as non-bonding electrons on the oxygen come down and are shared now between xenon and oxygen. And you're going to see how that changes the formal charge. Xenon still has that non-bonding electrons, that lone pair attached to it. And there you go. Now, the formal charge here, if we look at oxygen, would be 6 minus, and we have, it looks like 4 bonding electrons divided by 2. Remember, each line is 2 electrons, so for a double bond, that's 4. And then minus 4 of the non-bonding electrons, and now that's 0. And xenon is 8 minus, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bonding electrons divided by 2 minus 2, and now that's 0. And so this Lewis structure has minimal formal charge, and so that would be closer to the true form of the molecule. Now, we want to draw the molecular geometry. Like, that's the whole goal here, is to see in 3D, like we discussed in the previous video. So we need to count the electron groups attached to the central atom. How many do we have? 1, 2, 3, 4, 5, 6. Excellent. We have 6 electron groups, which is what electron geometry? Octahedral, good. But one of those groups is a lone pair, and therefore what is the molecular geometry? Excellent. Square pyramidal. And what's the bond angle? Approximately 90 degrees. Fantastic. So remember with square pyramidal, if we draw octahedral as a guide here, two are in the plane, just drawing the electron geometry, because remember we can replace those open circles and the central atom, or that dark circle with the central atom. The open circles are either bonded groups or lone pairs. So in this case here, I will mimic this. I'll put xenon as the central atom. That was the dark circle. I'll put the oxygen up top. And then I'll put the fluorines in. Remember, two going in the back. And then one lone pair. And so this illustrates something that is square pyramidal geometry. This is the 3D representation of this specific molecule here. And overall, would you say this is polar, nonpolar, or ionic? Definitely polar. Fluorine's very electronegative, xenon's not really, and then oxygen's pretty electronegative. So overall, this molecule is a polar molecule. Usually when it comes to ionic, we're looking at a metal and nonmetal, or for example, two polyatomic ions held together by that electrostatic charge. So this one is a covalent molecule, so we're just trying to identify polar and nonpolar overall. All right, let's do the next example, sulfur dioxide. And so sulfur and oxygen are each in group 6A. So 3 times 6, all right, if we said 6 plus 2 times 6, that's 18 valence electrons that we're working with here. Remember to first connect them as like a skeleton. Just the sulfur bonded to 2 oxygens, and you fill the outside atoms first. You fill their octet first. And right now, how many electrons have we drawn in total? Total is 16 electrons, good. But we have 18, so where do we put the 2 left over? On the central atom, on the sulfur. You wait to put electrons only if you have any left over after filling the outside atom's octets. Fantastic. And then the next thing we check out is, does the central atom even have an octet? And right now the answer is no. Sulfur only has 1, 2, 3, 4, 5, 6 electrons attached to it. It really wants 8. So what does it need to do in order to get an octet? Excellent. It needs to borrow electrons, right? It needs to borrow electrons from the oxygen. And so 2 of them are going to come in and share. Now, we did just learn in the previous example that an oxygen that's single bonded with 3 lone pairs has a -1 formal charge. I promise that's a negative there. Therefore, one of these atoms is a +1. It turns out it is the sulfur, because we saw an oxygen that is double bonded with 2 lone pairs is neutral formal charge. That's not going to change. So it's the sulfur here. And you can do that calculation to prove that to yourself. Now, it has formal charges. It does add up to 0, right? Which is the overall charge for sulfur dioxide. However, we have to ask ourselves, can the central atom break the octet rule? All right, so let me bring up the periodic table here. Sulfurs right here. And if you remember, when looking at quantum mechanics, that the energy level, the principal quantum number n, you can kind of count it here. So 1, 2, 3, 4, 5, 6, 7. Those are like the period numbers here. And you will notice that sulfur is located in N is equal to 3. Whereas carbon and oxygen and nitrogen and these elements here are located in N is equal to 2. And that's going to be a big difference. Like something that's in N equals 3 or greater, it's going to behave differently than something that's located in N is equal to 2. All right. So N is equal to 3. That means L, 0, 1 can have the possible values of 0, 1, 2. This is just from quantum mechanics. 0 represents as the s orbital, 1 represents a p orbital, 2 represents a d orbital, and in the s subshell you learn that you can fit up to 2 electrons. In the p we can fit up to 6, and in the d we can fit up to 10. So for elements that are in N equals 3 or greater, N equals 4, N equals 5, like they have these orbitals and all this space to fill in these electrons, and therefore they can break the octet rule. So sulfur can break the octet rule, and therefore it's going to want to minimize that formal charge. Whereas if we have something that is N equals 2, like carbon, L can only have 0 and 1 values. Remember, when you calculate L, it's always 0, dot, 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 and minus 1. And remember that 0 represents S, 1 represents P. Maximum we can fit in S is 2 electrons, in P, 6. So that's where you get that magic number 8 there for the octet rule. So for elements like carbon and nitrogen and oxygen, they cannot break the octet rule. So that's why when we will cover organic chemistry or an introduction to organic chemistry, you're going to hear me say, do not give carbon more than 4 bonds, right? That's never ever going to happen here. So sulfur can, and therefore like the previous example, we can share these electrons over here to help minimize formal charge, because I like to think of these types of elements, they're like a New York skyscraper. They have all these apartments to fill these people, whereas these types of elements have a much smaller space and less rooms to fill those electrons. Okay. All right. So if you look here, we're sharing those electrons. Now you can calculate the formal charge for sulfur. It's going to be 0 here. This is the true form. And the way I've drawn it, this is not true to form in terms of bond angle here. It's not linear. Remember, because it has a lone pair on the central atom. So how many electron groups are attached to the central atom? We have 1, 2, 3. So we're looking at something that is 3 electron groups, which is what electron geometry? Trigonoplanar, excellent. So that's approximately what kind of bond angle? 120. It's going to be slightly less than 120, right? Because of the lone pair. However, because it has a 1 lone pair, this is what kind of shape? This is bent, excellent. So we want to represent that. And it's true form. It's true 3-dimensional form with the 120-degree bond angle, or slightly less than 120 degrees. Would you classify this molecule as polar and nonpolar? Definitely polar, guy. It's going to have some sort of dipole moment. All right, in our last example here, how many valence electrons do we have for this very interesting molecule that I've drawn here? Good, you have 34 valence electrons, so 7 plus 2 times 6 plus 2 times 7 plus 1. So whenever you see a -1, you add that because it's an electron to the number of valence electrons. So 34. All right. Iodine will be the least electronegative, so it'll be the central. Fill the outside first, outside atoms, octets. And how many electrons have I drawn so far? 32. Very good. So you just count each bond as 2 electrons, and then 1, 2, 3, 4, 5, 6. That's 8 times 4 is 32. I put the 2 left over on the central atom because we started off with 34. Fantastic. Once again, you'll probably notice that this one has, oxygens that are single bonded with 3 lone pairs. These have a -1 formal charge. And iodine here has a +1 formal charge. So if you say 7 minus 1, 2, 3, 4, 5, 6, 7, 8 bonded electrons divided by 2 minus 2, that's the +1. Now, for this particular molecule, it needs to all add up to -1. And so we have -1 + 1, -1. So that does all add up to -1. But if we can minimize formal charge, this molecule will. And iodine's pretty low on the periodic table, so it can break the octet rule. So I'm going to share one of these oxygens, its lone pairs, and make a double bond, and that will help us to minimize formal charge. You're seeing a pattern here. Oxygens do like to make double bonds if it can. Now, there's still a -1 formal charge on that oxygen, and there has to be, right? Because this molecule is not neutral. So that's that -1 formal charge. Now, I sometimes have students say, well, what happens if I put this lone pair here, like make a double bond here? Then that means the iodine gets a negative charge. But out of the 2 elements, which one is more electronegative, iodine or oxygen? Oxygen's definitely more electronegative. It's much closer to fluorine, right? And so when you do end up having a formal charge, make sure to put the more negative formal charges on the more electronegative atoms. All right, so now it's important for us to determine the molecular geometry. How many electron groups are attached to iodine? We have 1, 2, 3, 4, 5 electron groups, which is what type of electron geometry? Excellent. Trigonal, bipyramidal. Fantastic. How many lone pairs on the central atom? 1 lone pair. So what kind of shape will we see here? Seesaw. Good. It's my favorite. All right, so now we need to, I'm going to draw the or the trigonal bipyramidal, just electron geometry, just so we have something to mimic. This always helped me when I was a student to draw in 3D. All right, so we're going to put the iodine in the center as a central atom. Where do lone pairs go in trigonal bipyramidal? The equatorial position. Good. So I'm going to put it here. Now, going back to your first general chemistry knowledge, which atom is larger, oxygen or fluorine? Technically oxygen, right? And so it's a bigger atom, so it wants more space. So if you were an oxygen atom, I'm going to personify our atoms here. If you were an oxygen atom, where would you be? In the axial position or the equatorial position? Excellent. You'd be in the equatorial. You want more space. So a lot of times when we want to represent, a double bond, like you see here, I represented the double bond kind of going back. So in that case, I made one of the bonds dashed, and then I put another line next to it to indicate that this is technically a double bond here. And make sure you always draw in your formal charges. At -1. So the bond angles for this one here are a little less than 90 degrees and 120 degrees. And would you classify this molecule as polar or nonpolar? Definitely polar. All right, that wraps up our discussion of drawing Lewis structures, talking about electronegativity to help us determine if something is polar or nonpolar, and deciding how to minimize formal charge and draw the final molecular geometry to determine the correct bond angles. Make sure you're practicing these types of problems. I hope that my strategy for approaching these problems will help you feel confident in drawing Lewis structures and deciphering molecular geometries and polarity and nonpolarity. Thank you for watching, and see you next time.